Bismillahir Rahmanir Rahim. Hello everyone, so today I would like to do a fluid mechanics derivation for the following scenario, an open flow down an incline. Okay, so you can see in my diagram I have a fluid flow down an inclined surface. So here you can see I've drawn a velocity profile. So you can see that the velocity profile consists of a number of streamlines. Each streamline has its own velocity. So there are a few derivations that we can do for this type of scenario. We can calculate the velocity at any point of the velocity profile for the fluid. We could calculate them. We could derive the maximum velocity, and we could also derive the sum of the flow rates. Okay. So before we do that, let's establish a few assumptions. So we assume that it's a steady flow. So the steady flow fluid, we assume that the velocity for each streamline is a constant. We also make the assumption that this flow is a laminar flow. So we ignore any turbulent effects. Okay. Another assumption that we make is that we ignore hydrostatic effects. So the static pressure for this fluid we assume to be constant. So in our velocity profile, we can see that the velocity at this point here will be 0. So here we assume that the velocity is 0 because the shear stress at the surface is at its maximum. So here we can write tau max. So the shear stress at the inclined surface is at its maximum. The shear stress at y equals d is equal to 0. Therefore, we can see that the streamline here is at its longest, meaning that the velocity is at its maximum at y equals d. So we can write those things down. So tau max at y equals 0. And we also assume that at y equals 0, u is equal to 0. U is the velocity. Tau equals 0 at y equals d. So at y equals d, tau equals 0, and our velocity u equals u maximum. So before we commence our derivation, we need to assess all the forces acting. So let's draw a shaded box in our velocity profile within our fluid. So in this shaded box, we can assess all the forces acting on it, and we could draw a free body diagram to have a better visualization. So here you can see I've drawn the shaded box. So now we can assess all the forces that are acting on this shaded box. So the shaded box has a height of dy and a length of dx. The width is dz going into the page, but since we're doing this as per unit width, we can ignore dz for now. Okay, so some of the forces acting on this shaded box. On the surface, you're going to have the shear stress, tau, and on this side here, acting in the opposite direction, we're going to have tau plus delta tau. And also you're going to have the mass of the shaded box, so the weight acting. So the weight we could write as mass times by the gravity, so we could write that as mg. So if we apply Newton's second law onto this free body diagram of force equals mass times acceleration, we can get the understanding that the net viscous force is equal to the body force. So let me write that down for you. So the net viscous force is equal to the body force. So the only body force is due to gravity for this free body diagram, mass times gravity. Okay, so now let's apply all the forces acting on our free body diagram to Newton's second law. Okay, so let's first do our net viscous forces. So the force due to shear stress acting this way, you can write here as tau, and on the opposite direction you're going to have tau plus delta tau, so minus tau plus delta tau. Now all of this shear stress, let's multiply that by the area, because we know that the force is equal to the pressure times area. So the area will be dx times by dz, which is the width going into the page. But since we're doing per unit width, we can ignore dz for now. So let's multiply all of this by dx. Okay, so all of that will equal to the body force. So as we discussed before, that the body force will only be due to gravity. So the body force will be acting this way. This will be mass times gravity times by sine theta. So mg sine theta, if we do our mechanics properly. So let's neaten this all up. So tau minus tau will be 0, so we're left with delta tau dx on this side, delta tau dx, and that will be equal to mg sine theta. So delta tau mathematically we can write that as being equal to delta tau with delta y dy. So the reason why it's minus is because tau is decreasing as y increases, as we discussed earlier. Okay, so let's put that into delta tau. So minus delta tau over delta y dy times by dx is equal to mg sine theta. So what we also have to know is that Newton, one of his laws of viscosity, he established that tau is equal to mu du over dy. Sorry, mu delta u over delta y. So we can substitute our tau into here. So we could get this minus delta over delta y, bracket all of this, mu delta u over delta y times by dy dot dx, and all of that is equal to mg sine theta. Okay, so now let's multiply our differentials. So delta times by delta u, this will give us minus delta squared u over delta y times by delta y, that will give us delta y squared. And oh yeah, don't forget the mu. So now all of that times by dy dot dx, and all of that is equal to mg sine theta. So we also know that the mass is equal to the density times by the volume. So the mass we can write as delta times by the length times by the width and times by the height. So times by dx, dy and dz, but since we're doing per unit width, we don't have to include dz. And all of that times by gravity times by sine theta, times gravity times by sine theta. So now you can see we can cancel out dy and dx from our two sides. Cancel out dy, cancel out dx. So now we're left with, if we neaten this up, minus mu delta squared u over delta y squared, and all of that is equal to rho g sine theta. So let's take mu to the other side so we get our derivative on its own. Okay, so if we take our minus and mu to the other side, we should get delta squared u over delta y squared. All of that should be equal to minus rho g over mu times by sine theta. Okay, so we want to get our velocity on its own. So what we can do is we can integrate twice. Okay, so if we integrate once, we should get delta u over delta y, and that should be equal to minus rho g over mu sine theta dot y plus our constant if we integrate once. So now to get u on its own, we can integrate a second time. So integrate twice. So now we should get u is equal to minus rho g over mu sine theta y squared over 2 dot y squared over 2 plus c1y plus our second constant c2. Okay, so now we've got u on its own. We can establish some of the boundary conditions we discussed earlier to work out our constants c1 and c2. So from our diagram, we established that at y equals 0, the shear stress will be at its maximum, so we assume the velocity to be 0. So let's write this condition here. At y equals 0, the velocity u will also be equal to 0. So if we put all of that in, we should get u, and u is equal to 0, y's are also 0, so this should all be 0, plus c1 times by 0, that should give us 0, and we're left with c2 plus c2. So from this, we know that our constant c2 is equal to 0. Okay, so now we need to work out our constant c1, so we can apply our second boundary condition. So if we go back to our diagram, so we established that at y is equal to height d, we know that the velocity is at its maximum. That's because the shear stress is at its minimum. So we can assume, because the shear stress is very low, we can assume the shear stress to be 0 at this point. So if we go to our previous derivation that we did, from Newton's law of viscosity, tau equals to mu, which is our constant, times by delta u over delta y. We know at y equals d, the tau is equal to 0. Therefore, we can write delta u over delta y as being equal to 0. So we could write our second boundary condition, that at y is equal to d, we know that delta u over delta y is equal to 0, as tau is equal to 0. So if we apply this to our equation again, our equation here, so delta u over delta y is equal to 0. So 0 is equal to minus rho g over mu sine theta times by y we established to be as d plus our constant c1. So from this we could work out c1 to be equal to rho g over mu sine theta times by our d. So going back to our equation for our velocity and putting in our constants c1 and c2 in, we have derived our equation for velocity for our velocity profile. So we can write this as u is equal to minus rho g over mu sine theta y squared over 2 and we have our constant c1. So let's write here so we have more space. C1 as rho g over mu sine theta dot d, and our constant c2 is equal to 0. We could write our equation a lot more neater if we factorize. So we could write this as u is equal to rho g over mu sine theta square brackets yd minus y squared over 2, if we've done our factorizing properly. So let me put my box around this one. So this is my final equation, actually, a more neater version of what I wrote before. Okay, so the next derivation we could do is quite a simple one, is for our maximum velocity. So if we go back to our velocity profile, we established that at y equals d, we assume the shear stress to be 0 since it's very, very small, so we assume it to be negligible. So at y equals d, we assume the velocity to be at its maximum. Okay, so we could write this condition here. At y is equal to d, the velocity u is equal to u maximum. So if we substitute all of that into our earlier derivation of velocity, we could write all of this as u max is equal to rho g over mu sine theta bracket d squared minus d squared over 2. So if we simplify that, d squared minus d squared over 2, that will give us d squared over 2. So we can write u max, maximum velocity, will be equal to rho g over mu sine theta plus square brackets d squared over 2. So let's box our second derivation. So this is the derivation for our maximum velocity. Okay, so the next derivation we could do is for our volumetric flow rate. So our volumetric flow rate, q dot, that will be an integral of our velocity dy within our limits of d, which is the height, and 0 at y equals 0 of our plane surface. So if we substitute our equation into u, which we derived earlier, we could write q dot is equal to the integral between our limits d and 0 of rho g over mu sine theta square brackets yd minus y squared over 2 dy. So if we integrate this, we should get all of that being equal to rho g over mu sine theta bracket y squared d over 2 minus y cubed over 6 between our limits d and 0. So if we put our limits d and 0 into our equation, we should get our third derivation for our volumetric flow rate. So Q dot, we could write that as being equal to rho g sine theta over mu. If we get our fractions right by putting d in, and 0 should all cancel out, bracket d cubed over 3. So here is our third derivation for the volumetric flow rate. So let's put that into our little box here. Okay, so now for the final derivation, we could do it for our average velocity for our whole velocity profile. So in one of my previous videos for a viscous flow between two parallel plates, I established the relationship between the maximum velocity and the average velocity. So the ratio between the average velocity and the maximum velocity, so this is the average velocity of our Umax, we established that to be 2/3. So you can see the derivation for that in one of my previous videos on viscous flow between two parallel plates. So we also now know that the average velocity is equal to our flow rate over the distance d. So all of that will be equal to our volumetric flow rate, which we derived earlier, rho g sine theta over mu d cubed over 3, so that will cancel out with d, so you will be left with square bracket d squared over 3. So now we could do our dashed box for our final derivation for our average velocity. Let's do it for this one as well. So this derivation you can see on my previous video. So there you have it, guys. Our derivations for our open flow down an incline.